welcome friends to this second lecture of module 4 and of this NPTEL course of environmental soil chemistry, and in this lecture we will be discussing about the different how to calculate the different species of ions in the soil, as well as we will be talking about ionic activities and their implications, and also we will be talking about the stability diagram. Now, in the previous lecture we are talking about the speciation of the soil solution, and I started on one example, if you remember. So, let us continue that. In that example we started to calculate the we were basically calculating the concentration of different calcium species present in the soil solution from a basic soil, and we assumed that at a pH of 7.9, when the total calcium concentration was 3.715 multiplied by 10 to the power minus 3 mole per liter. So, we assume that the calcium occurs as either free hydrate, as free hydrated calcium 2 plus ion, or as complexes with inorganic ligands like carbonates to form calcium carbonate, sulfates to form calcium sulfate, and chloride to form calcium chloride. Okay. So, I showed you that then we have presented this the sum of the free and complex ion in this form of equations, and then we have shown the conditional stability constant or conditional equilibrium constant for each of these complex forms like calcium carbonate, then calcium bicarbonate, then calcium sulfate and calcium chloride. Okay. We have expressed them in the forms of in terms of conditional stability constant or conditional equilibrium constant. And then by taking this calcium 2 plus as a common factor, we have converted this total equation in the form of this algebraic equation, where we can multiply the conditional stability constant of each of these each of this compound with their concentration of that particular ligand. So, for example, you can see K1 conditional, that means the conditional stability constant of calcium carbonate multiplied by the concentration of the ligand or carbonate, similarly for bicarbonate and then sulfate and chloride. So, basically we have reshaped that the equation in the form of conditional stability constant. Now, we want to calculate this total relationship by inputting the values of this conditional probability constant. Now, we have already used several models. There are several computer models which have this database of this conditional probability constant. So, I was giving you an example using one particular complex. Let us consider this calcium bicarbonate, and in this calcium bicarbonate we can see that calcium plus H plus carbonate forms this calcium bicarbonate. So, in this calcium bicarbonate, if we know the conditional stability constant, that is 9.33 into 10 to the power 10 at 298 Kelvin temperature, we can express this equation in like this, the concentration of calcium bicarbonate is basically 9.33 into 10 to the power 10, and concentration of calcium, concentration of H plus and concentration of carbonate. Now, if we input the concentration of calcium, concentration of protons or H plus and concentration of carbonate, then we can calculate the concentration of that particular compound. So, by the way, this similar way we can calculate the concentration of each and every compound which is present in the soil solution. So, once the free concentration, so what I mean that once this free concentration of Ca2 plus, H plus and CO3 plus are determined, the concentration of the complex, that is calcium bicarbonate, can be calculated. So, the calculated concentration of various metal species, for example, calcium carbonate, calcium sulfate, calcium chloride, calcium phosphate, calcium nitrate, calcium hydroxide. So, all these can be checked by inserting them into the mass balance equation and determining if the sum of the equal to the known total concentration. So, basically once we calculate the concentration of calcium carbonate, calcium sulphate, calcium chloride, calcium phosphate, calcium nitrate, calcium hydroxide and input those values, and then we can see whether the summation of all these is equaling to the CAT. Then we can see that yes, this is the correct calculation. So, let us see one example. So, in this table we can see the concentration of free metals, free ligands and then total metal complex by each ligand and total concentration of metals and ligands in such solution. So, in our case we know that our total concentration of metal of calcium is 3.715 multiplied by 10 to the power minus 3. So, the total metal complex by each ligand in case of carbonate is this, is sulphate, chloride, phosphate, nitrate, hydroxide, and free metals is this. So, inputting these values, if we input these values, all these value, we can see basically the calculation is coming around 3.715 10 to the power minus 3, which is almost equal to 3.717 10 to the power minus 3, which is the value of CAT. So, this is how we calculate the sum of free ions and complex species from the model, and then we can see that is the close to the CAT values. So, again how we start? We start by inputting the conditional probability constant from the models, and by inputting the conditional probability constant, and then we calculate the individual species concentration of the individual species, and from there we can see the concentration of the compound, and from inputting the values of the concentration of the compound from the table, we can see if their summation is equal to the total total metal concentration or not. If these are two same, if these two are same, then we can see that okay, these are the concentration of individual. We have seen that this is the justified speciation of that particular metal in the cell solution. So, then let us consider another important thing, that is ion activity and activity coefficients. So, the single ion activity coefficients are basically activity coefficients are calculated using the extended Debye-Hackel equation. So, the extended Debye-Hackel equation, we can calculate this activity coefficient, where this log of activity coefficient is basically minus a Zi square I to the power half plus 1 BAI I to the power half, where A and B are the constant relating, these A and B are the constant related to dielectric constant of water, and generally we take their value as 0.5 and 0.33 at 298 Kelvin, and AI is basically the size of the ion in angstrom, Zi is basically the charge or the valence of the ion in solution, and I stands for the ionic strength. So, ionic strength basically is a measure of a degree of interaction between the ions in the solution, and it is related to total electrolyte concentration and is expressed as basically in the form of this summation, where Ci basically relates to the concentration of ith species in mole per liter, and Zi is basically charge or valence of the ionic species, where this summation extends all over the ions in the ions in the solution. So, whatever ions are present, we can sum them for this for their respective concentration as well as their charge or valence squared, and then we can get the total ionic strength. So, if we consider the ionic strength of different different ions, for example, in case of H plus, values of single ion activity coefficients at various inorganic, various ionic strength at 298 Kelvin. So, we can see in case of H plus, we we get their ionic strength, single ion activity coefficient, basically the single ion activity coefficient, how their coefficient changes based on the ionic strength. Okay. So, at different ionic strength and particular ionic radii. So, for this lithium, then sodium bicarbonate, then orthophosphate, and all these we can get their values of the activity coefficients from this table. So, and also this is for the inorganic ions of a charge of 2 plus, as you can see Mg2 plus, beryllium, calcium, copper, zinc, then tin, and then iron, then nickel, cobalt, and so on and so forth. And this is inorganic ion of charge 3 plus, as you can see L3 plus, Fe3 plus, then chromium 3 plus, selenium 3 plus, and so on and so forth. So, what is the relationship between the ion activity and activity coefficients? So, when the ionic strength is greater than 0.2 mole per liter, the single ion activity coefficients are basically calculated from extended Debye-Hückel equation derived from the actual values, which I have seen recently. However, for more concentrated solutions with ionic strength less than 0.5 mole per liter, we generally follow Davis equation, and this Davis equation generally take this form of log of activity coefficient equal to minus a z I square, then I to the power half 1 plus I to the power half minus 0.3 I is the ionic strength, whereas a is the constant and Z I is basically the valence or the charge. Okay. So, let us see some example mathematical solution, some sample problems of calculation of ionic coefficients. So, here the first question says the calculate the I for 0.10 mole per liter for potassium nitrate and 0.10 mole per liter K2SO4 solution. So, I for 0.10 mole per liter potassium nitrate, we can use this formula where Ci we already know that the concentration is 0.10 mole per liter, and in case of potassium it is plus 1, and in case of nitrate it is minus 1. So, we get the value of 0.10 mole per liter, and I for basically 0.01 mole per liter K2SO4. If you want to calculate it for the K2SO4, obviously then it will be basically 2 into into 0.10 plus 1, because it is K2, and then SO4, we know that SO4 has the valency of minus 2. So, it will be squared. So, 0.10 plus minus 2 whole square. So, we are getting a value of 0.30 mole per liter. So, this is how we can calculate I from the concentration, from the valency of the cations as well as the associate anions. Now, another question is calculate the activity coefficient for cadmium 2 plus at 298 Kelvin when the ionic strength is 0.01 mole per liter, and we can extend we can use the extended Debye-Hückel equation. We can input those values. We know that minus a, that means it is basically 0.5. We have already seen we are using the default values of 0.5 for A, and for B we are using the value of 0.33. These are two constant based on the dielectric constant of solution, and then cadmium Z I square. So, from there we can also using this formula we can calculate that 0.17 and then log of value, and from there we can get the value of 0.67. Okay. Again we are basically using minus a Z I square plus 1 plus b a I and then I to the power half. As you can see, we are using 0.01 value of ionic strength here, and this is 0.33. We are using the value of B constant, which is basically depends on the dielectric constant of the solution. So, this is how you solve the ionic coefficients and ionic strength calculations. So, another thing generally comes to our mind, what is the difference between dissolution and solubility processes. Now, there is a difference between these two terms. One, dissolution is basically dissolving of a soil solid into the soil solution, whereas solubility is the process of deposition or precipitation of a substance from the soil solution. So, again dissolving of a soil solid into the soil solution is known as the dissolution, whereas solubility is the process of deposition or precipitation of a substrate from the soil solution. And in case of dissolution, it occurs only when the soil solution is undersaturated. However, the solubility occurs when the soil solution is supersaturated. So, basically these are two opposite processes. In case of dissolution, soil solution has less solute than in equilibria. However, in case of solubility, soil solution has more solute than in equilibria. So, as a result of that, due to the supersaturation, there is a precipitation or there is deposition. However, when there is a less strength or less solute than in equilibria, obviously there will be further dissolution to maintain the equilibrium. Now, dissolution and solubility basically determine the fate of inorganic mineral components of the soil, and dissolution, precipitation, equilibria affects the weathering, as you know, soil formation and the contaminant mobility. Obviously, this dissolution and precipitation highly control the concentration of differing concentration of different solid phases in different stages of the weathering, whether they will further weather away or not based on this dissolution and solubility process. Obviously, due to the solubility of different minerals, the weathering basically goes on, and when there is no further solubility of the mineral, obviously the weathering process stop there. Okay. And also soil formation basically depends on this dissolution and solubility and precipitation also, and contaminant mobility is also depend on this dissolution and solubility process. Now, in case of calcareous soil like gypsum dissolve relatively rapidly and congruently. Now, congruent mean after dissolution the stoichiometric properties in the solution are same as those in the dissolving mineral. So, basically when calcium and sulphate combines together to form the calcium sulphate or gypsum, it is a stoichiometric, the stoichiometric proportion remains same. So, this is how this reaction is known as the congruent reaction. However, many soil weathering reactions are incongruent also, and this is due to the precipitation of a new solid phase. Because when there is a reaction and formation of a new solid phase, when that solid for example, when there is a reaction between two species and the new species which is being formed is getting precipitated as a new solid phase, then either separately or on the surface of the original mineral undergoing dissolution, then it is obviously changing the stoichiometric proportion, and as a result this is called incongruent process. Now, silicate minerals, in case of silicate minerals, they dissolve to form various secondary minerals. For example, as you can see in this slide, obviously anorthite, which is an important silicate mineral, or this is an important feldspar also, calcium feldspar. When they are reacting with the carbon dioxide or water, in other words the carbonic acid, when they are reacting with the carbonic acid, they are forming the kaolinite. So, this is basically dissolving the primary minerals to form a secondary minerals. As you know, the secondary minerals are formed from the primary minerals. Here you can see that anorthite, which is a calcium feldspar, is getting dissolved in the presence of carbonic acid to form the kaolinite, and also they are producing the calcium ion as well as the bicarbonate ions. Also, you can see here albite, also when they are combining with the carbonic acid, they are forming the smectite, and also they are forming the sodium ions, bicarbonate ions and silicic acid. And also biotite, when they are reacting with the oxygen and carbonic acid, they are forming gibbsite, goethite, potassium ions, magnesium ions, bicarbonate ion and silicic acid. So, you can see that how the dissolution of different primary minerals basically helps in development of different secondary minerals into the soil, and that is why this dissolution on solubility process are very important for the formation of the soil as well as for the weathering process. Now, in case of silicate minerals, water and carbonic acids are the major reactants as we have already seen, and calcium, magnesium, potassium, sodium and bicarbonate are released into the soil solution, which we have just seen, and the extent to which these reactions occur depends on the soil forming factors. Obviously, due to the presence of different climatic condition, whether there is a warm and humid climate, whether there is a presence of acids, mild acids which are exuding from the plants, or whether there is a presence of presence of other factors, basically also topography basically also also determines the dissolution in solubility process. Now, what is the thermodynamic dissolution constant? Now, considering the following dissolution reaction in gibbsite. So, this is a gibbsite. When it is reacting with the proton in acidic environment, they are basically forming the aluminum as well as water. So, the thermodynamic dissolution constant, which is K0Ds from this reaction, is basically can be expressed in terms of this. Okay. So, this is called the thermodynamic dissolution constant. Now, thermodynamic dissolution, so the activity of any solid phase is defined as 1 in its pure form when there is no structural imperfections. So, consider that the activity of any particular solid phase is defined as 1 when when it is pure form, when there is no structural imperfections, a standard temperature at 298 Kelvin and pressure of 0.101 megapascal, and the activity of water is also considered 1 since soil solution are indefinitely dilute compared to the concentration of water molecules. So, assuming the activity for aluminum hydroxide and water as 1, this thermodynamic dissolution constant becomes this can be simplified to this. Also, this ratio is known as the thermodynamic solubility product constant. So, this is also known as the thermodynamic solubility product constant. Now, the thermodynamic solubility product constant is numerically equal to the thermodynamic dissolution constant when the solid phase is pure and aqueous solution phase is infinitely dilute. Obviously, these are two conditions, because in these both the cases the activity will be 1. So, the ratio of L3 plus H3 plus is often referred to the activity product or ion activity product. Okay, we are basically seeing the ionic activity. So, when the ratio of this ionic activity product by this this K0SO, that is equal to 1, then the solid solution is in equilibrium with the given solid phase. When this ratio becomes greater than 1, then the solution is then supersaturated with respect to the solid phase, and when this this ratio is less than 1, the solution is undersaturated with respect to the solid phase. So, again if we go back and see, this is the thermodynamic dissolution constant, and thermodynamic dissolution constant can be represented in this simplified form in the form of a solubility product constant when the activity of the solid phase is 1 and the activity of the solution phase is 1 because it is dilute, and then we can see that in this condition these two values, these two constants are same, that is thermodynamic dissolution constant and thermodynamic and the solubility product constant is same. So, this ratio of the activity of L3 plus and H plus is often referred to as the ion activity product, and these ion activity product by this constant, when it is equal to 1, then the soil solution is in equilibrium with the given solid phase. When it is greater than 1, then it is supersaturated, obviously with respect to the soil solution phase. When it is supersaturated, obviously there will be precipitation, and when it is less than 1, the solution is unsaturated, and then further dissolution will go on for maintaining the equilibrium. Now, for seeing this whole process, we generally use that stability diagram. So, stability diagram are used to determine, or two basically, stability diagrams gives us two basically answers. One is, does a solid phase control the concentration of an element in the soil solution, and if it does, what the solid is. So, they are constructed by converting previously solubility relationship into logarithmic terms and rearranging the terms from a straight line relationship. So, as you can see, the log K0 d, that is thermodynamic dissolution constant, can be calculated from the standard free energy accompanying the reaction, which is denoted by this. So, if it is the standard free energy of formation is basically the the can be calculated by this equation. Okay. Now, this is basically the standard summation of the standard free energy of all the products and minus the summation of standard free energy of all the reactants. So, considering the in case of gibbsite, we can see that when the gibbsite is reacting with the protons, it is producing L3 plus 3H2O. We already have seen this. So, using the published values, we can calculate the value of this particular delta G0, which is minus 45.92 kilojoule per mole. So, as this delta G0 is related to the thermodynamic dissolution constant, this delta Z0 can be related to the thermodynamic equilibrium constant with this formula, where this R is basically universal gas constant and T is the absolute temperature. So, this is the relationship between this thermodynamic equilibrium constant and this this delta G0, and again for your recap, this delta G0 is basically this delta 0 is nothing but the standard free energy of the formation, and we calculate this delta G0 by summing up the delta G0 of all the products and delta G0 of all the reactants. The standard free energy, remember, this is the standard free energy of formation. So, this is how we can relate this standard free energy of reaction to the thermodynamic dissolution constant. Now, this thermodynamic dissolution constant used by inputting all the values of this, that means R, T, Ln, K, K0 d. So, basically when you input all these values, we will get this value of minus, we will get this reaction, we will get this equation. So, for the pre-calculated value of delta G0R, we know that the value will be 8.04. So, the corresponding solubility line is determined by plotted as. So, we can see that once we calculate this log value of K0, we can calculate this, and from there we can express this straight line equation. Again, let me go back and describe it again. We know that thermodynamic equilibrium constant can be, or the thermodynamic dissolution constant is basically the K0 this, and the log of K0D's values can be calculated from the standard free energy accompanying the reaction, and the standard free energy accompanying the reaction can be calculated by the standard free energy of the products minus standard free energy of the reactants. So, considering, if we consider particular this case of dissolution of gibbsite to form the aluminum as well as water, we can use the published values of this free energy of formation, and the free energy of formation we can see it is minus 45.92 of, we can use this formula of free energy of the products and free energy of the reactants. We can calculate this value of the free energy of the thermodynamic free energy of the reaction, and we know the relationship between the thermodynamic dissolution constant and this thermodynamic free energy of reaction can be related using this formula, where this R is the universal gas constant and T is the absolute temperature in Kelvin. So, by inputting all these values we can get this relationship, and from the pre-calculated values of delta G0 for gibbsite we can input these values and we can get this log of this thermodynamic dissolution constant of 8.04. From there we can calculate this linear equation. So, stability diagram, basically here in the linear equation, if this log of L3 plus is our we can use this as y axis, this is the intercept, and obviously minus 3 is the slope. So, we can see that log L3 is plotted on the y axis, pH is plotted in the x axis, and minus 3 and 8.04 are the slope and the y intercept respectively, and from there we can see the solubility, this is called the solubility diagram of various aluminum oxides and hydroxides, and we can see the solubility of different elements like conundrum, amorphous, LOH3, biarite, gibbsite, Nurstandite, and then bohemiite and diaspore and all this. Okay. So, this is called the stability diagram. Now, the advantage of a stability diagram is that the solubility of several different solid phases can be compared at one time, and the position of the different lines correspond to the solubility of each solid, and the line nearest to the axis is the most insoluble or most stable. So, the lines which are nearest to these both axes are basically the most stable or most insoluble. So, the anhydrous aluminum oxides, as you can see here, the anhydrous aluminum oxides like gamma alumina and alpha alumina, as you can see from here, the gamma alumina and alpha alumina are not usually formed in soils because as they are high temperature minerals, and the order of decreasing the solubility among the remaining mineral is biarite. So, here you can see the biarite, and decreasing the solubility means it is the least soluble, followed by bohemiite and then Nurstandite and then gibbsite and then diaspore. So, obviously, the activity of L3 plus is dependent on the pH, and it decreases 1000-fold for every unit increase in pH. As you can see, at every unit increase in pH, the activity of L3 plus decrease 1000-folds. So, using the stability diagram we can see which mineral form is stable at which condition, and we can basically see the composition, or we can basically identify the dissolution of solubility of that particular element at that particular pH condition. Okay. So, for phyllosilicates, the stability diagram is plotted instead of log silicic acid at x axis and log aluminum plus 3 pH as the y axis. So, you can see this is the kaolinite when it is reacting with the acidic environment with the protons, it is producing aluminum, it is producing the L3 plus and silicic acid and H2O, and associated KD is basically 5.45. from there rearranging the terms and assuming an inactivity of 1 for water and kaolinite basically yields this value of 10 to the power 5.45, and taking log on both the sides solves and basically yields this reaction log Al3 plus 3 pH equal to 2.73 minus log H4 SiO4. So, basically we plot H4 SiO4 or log of this silicic acid in the x axis and log Al3 plus 3 pH in the y axis, and this is how the stability diagram of different minerals can be found, various primary and secondary minerals in the soil. So, the vertical lines, as you can see, silica, amorphous, amorphous, silica, quartz. The vertical lines are quartz and other sources of silica straight lines. This is because there is no aluminum in the crystalline structure, hence the dissolution reaction is essentially independent of the pH, because it is not dependent on aluminum. So, stability diagram are very useful in predicting the presence of stable solid phases in different soil solid system, and the portion of the straight line relationship close to x and y axis represent the most stable mineral phase of the most insoluble mineral. 2:1 type of clay mineral like montmorillonite are stable only when the concentration of silicic acid solution in solution is controlled by the solid phase and more soluble than quartz. So, this is basically the stability diagram and how we calculate the stability diagram and how we interpret the stability diagram. Let us wrap up our lecture here, and in the next lecture we will be talking about the surface complexes and different types of adsorption isotherms. Thank you very much.